అది కేటిచ్చు. We'll start at 3:30, 1 minute more. Hello. Good morning, everyone. Good afternoon, rather. This is Praveen J. You may call me PJ, sir. I have been working with Seekers for more than 10 years as a physics teacher, maths and physics teacher. So here I'm asked to teach physics for you guys. Probably starting today, I'll be teaching you physics continuously. And we are here to learn kinematics today. Kinematics is completely not a new topic to you. You had already started learning kinematics in your class 9 under the heading of motion in one dimension. So we'll basically just continue from there, or maybe develop upon whatever you have learned in your 9th standard. Okay, kinematics is one of those branches of physics that deals with motion and the relation between motion parameters. Now, we can start with basic definitions. Say, what is motion? Motion is something that you observe when you see a change of position in some object. Say you are looking at an object and you define its position by using a vector. In time, if the position of the object seems to change, then you say that the object has attained some motion. It has moved. As a verb, you say it has moved, or you say it has attained a state of motion. It's a state, right? Now, kinematics is a branch of physics that deals with studying motion and studying the relation between motion parameters. What are motion parameters? Motion parameters are those quantities that you would want to study, measure, and try to relate among each other to describe or to study the amount of motion present in an object. To describe motion, we need to make some measurements. Those quantities that we measure to study or describe some motion are called motion parameters. For one thing, you know, position is a motion parameter. Position of an object. You can define position of an object in any way, and mathematically we had been using coordinate systems to describe position of an object. A coordinate system, you already know, could be of 2 or 3 types. The basic coordinate system that you had learned is something called Cartesian coordinate system. This. A Cartesian coordinate system makes use of reference axis, straight lines that are perpendicular to each other. Obviously, they meet at a point called origin. That point origin is called the point of reference. We take it as 0. In a one-dimensional coordinate system, the point origin is described as x is equal to 0. In a 2-dimensional coordinate system, to describe position of objects on a plane, you take 2 reference axes that meet at a point origin, and we call the coordinates of the origin as 0, 0. We put it in braces, in brackets, small brackets. in a three-dimensional coordinate system, also called spatial coordinate system, where you try to describe motion of an object in space, not necessarily on just a plane. Then you use three coordinate axes as reference lines, and then the point of their intersection is the origin, and it is described with the point 0, 0, 0. Okay. This is basically the part of mathematics that you have learned in a chapter called coordinate geometry. In 10th standard you have learned. So a Cartesian coordinate system basically looks like that. And then there are other coordinate systems like polar coordinate system. I'll give a basic relation between polar coordinate system and Cartesian coordinate system. Polar and Cartesian are different, they are not same. Okay. If this is a Cartesian coordinate system, a plane, I'm drawing a planar coordinate system, an x-axis, a y-axis, and origin. If a point is written as x comma y, let's say the point is A, then OA is the distance of the point from the origin. If I draw perpendiculars from A to x-axis and to y-axis, then these lengths of perpendiculars are basically the abscissa and ordinate of the point, the coordinates. The distance of the point from the origin along the x-axis, this one, is called x-coordinate. The distance of the point from the origin along y-axis, this one, is called y-coordinate. Anything to the right of y-axis is measured as a positive x-coordinate. Anything to the left of y-axis is measured as a negative x-coordinate. Any distance above x-axis is measured as a positive y-coordinate. Any distance measured below x-axis is measured as a negative y-coordinate. The same point, if I write it in a polar coordinate system, it looks like this. A polar coordinate system does not have this line. A polar coordinate system basically has a reference point O, and it has a reference line, reference ray, you may call it x. Only x is there. The point A, which lies here, is actually characterized by two coordinates here also. The two coordinates are one, a distance called r, an angle called theta. Now this distance r is nothing but the distance of the point from the reference point O. Quite simple. This is r. And theta is the angle made by line OA or the ray OA with the positive x-axis, this one, in the anti-clockwise direction, this way. Right? Theta is the angle made by OA with positive x-axis in the anti-clockwise direction. This angle is called theta. So obviously, if you measure the angle from OX in the clockwise direction, you will read it as a negative angle. Okay, so this R and theta. Now, if you basically try to combine these two diagrams, you would understand that this length here, hypotenuse of this right angle triangle, is nothing but R. So basically, R is equal to root of x square plus y square. Similarly, this angle here, marking here, this angle is nothing but theta. So you could say tan theta from basic trigonometry, tan theta is equal to y by x. So if you are given the values of x and y, you should be able to find r as well as theta. Also, if you know the values of r and theta, you should be able to find the values of x and y. How? Basically, you draw a perpendicular from here, and this distance is nothing but y, and this distance is nothing but x. If this is r is known and theta is known, then y is nothing but r sine theta, because it's the opposite side. R is given and theta is given, then x is called as r cos theta. That is basically the x component, the component of r along x-axis. Right? I hope you are able to understand here. And we are cleaning up. If you want to take a screenshot, you take a screenshot now. I'm going to delete or clear the board in a small while. Right, now I am going to clear the board. Okay, so what we have learned is in the coordinate system, if x comma y are the Cartesian coordinates, they may be related to the polar coordinates r comma theta as x is equal to r cos theta and y is equal to r sin theta. Or the other way around, if you know r, if you know x and y, how do you find r and theta? R is equal to root of x square plus y squared, and theta is equal to tan inverse of y by x. Be careful with these inverse trigonometric functions. You may have to learn more about them in mathematics in the coming chapters. You will learn. So that is basically about position as a motion parameter. Okay, I'll make a table here. We were looking at motion parameters. first motion parameter that we saw was position of an object. Now, position of an object can be expressed as a point in two different ways, two or more different. There may be more different ways, more coordinate systems. We are sticking to the two-dimensional Cartesian coordinate system, x and y. Okay. Now, using vectors, any point x comma y on an xy plane may be written as x I cap plus y j cap. I am assuming that you did not learn vectors until now, so I'm not going to elaborate on this right now. So for now, we'll stick to kinematics. So we can skip it for later also, but remember this, that you have to study about vectors a little more. How to represent a vector on a Cartesian plane. Okay, so yeah, we'll keep it there. We'll keep it aside. So position is a motion parameter. Any change in position basically causes an observation that an object has moved. Okay. Second one. Motion parameter that we are going to look at next is the distance, basic distance that you probably would have heard of already. Distance is denoted by small letter d in most textbooks. What is distance? As a definition, distance is defined as the length of the path taken by an object. When an object is moving, the length of the path that it travels is what is called as distance. Now we have to be very aware how we are defining distance here, because you already probably heard of another quantity, displacement, and there's something called length, and it might be confusing among these quantities. Between these quantities, it's very confusing what it means, what else. Now distance means length of the path, meaning if an object starts from A and goes to B, without knowing what path did the object take to go from A to B, there is no way in which we can calculate or measure the distance taken by the object, traveled by the object. If you know the path, if this is the path taken by the object to go from A to B, then you may have to measure the length of the path. How do you measure the length of the path? You have to measure along the path. Along the path, you have to measure the total length. In your younger classes, you might have learned that if you know how to measure the length of a curve, you have to place a string exactly over the curve carefully, and then mark the first point A and the last point B, and then you remove the string and measure the length between those points on a scale. That will give you a simple way to measure the length of a path. You know how to measure the boundary of India, let us say. Like India has defined boundaries, but it's not all straight. It's rather curved. So when you buy a map from a stationery shop, you see the outline shape of India with a map clearly. The boundary is clearly marked there, right? And it is also mentioned there something called scale of the map. Scale of the map is usually written as 1 centimeter is to 100 kilometers, like that. I'm just giving an example. These are not exact numbers. 1 centimeter is to 100 kilometers. What does it mean? It means 1 centimeter length on the map is equivalent to 100 kilometers of length in reality, right? So if you have to measure the total boundary length of India, all you have to do is take a string, start from any point on the boundary of India, try to place the string very carefully along the boundary of India, and then try to come back to the same point again. And then you remove the string, make it straight, place it along a ruler, and measure the length of it. As many centimeters as it is on the scale, so many 100 kilometers it is on the real boundary of India. You get it? So basically distance is length of the path, and clearly distance is a path dependent function. It is basically like the name itself suggests, distance is a path dependent function. It is something that depends on the path. If the object had taken another path this way, the distance traveled by it would be different. If the particle took another path to travel like this from A to B, the distance traveled would be different. What if the particle took a straight line to go from A to B? Yes, the distance would be again different. So the distance traveled by an object or a particle to go from a point to another point surely depends on the path, and unless you know the path, you will not be able to measure the distance calculated by, traveled by an object. Okay. Now, if you think about it, say there is a timeline, right? Let us say this instant is t equal to 0 until some time we are calculating this. Let us say this is t equal to 1 second, 2 seconds, and 3 seconds, and 4 seconds, and etc. Okay. Let us discuss like this. say the object is here at t equal to 0. In 1 second, let us say the object moved 3 meters in this direction. It has come here. So you would say in 1 second the object has traveled 3 meters. In the second, t equal to 1 to t equal to 2. In the second, let us say the object moved this way. Please look at the screen. Let us say in the second, the object has moved this way, say 2.5 meters. You would say in the second, the object covered a distance of 2.5 meters. But what would you say the distance covered by the object in the first 2 seconds from t equal to 0 to t equal to 2? In the first 2 seconds, what is the distance traveled by the object? It should be 3 plus 2.5, which is 5.5 meters. You should not measure this straight line distance and say, see, this is initial point, sir. This is a final point, sir. So I'd rather measure the straight line distance between them and express it as distance. No, you can't do that. Because you know the path. It took a 3 meter length this way and then it traveled a 2.5 meter distance this way. So clearly the object has traveled 5.5 meters in the first 2 seconds of the path, 2 seconds of the travel. In the third second, if the object traveled like this, from the point at 2 seconds back to the initial point. In the third second, if it had traveled this distance, then in the first 3 seconds on the whole, the object has returned to its initial point, this point again. That does not mean the total distance traveled by the object is 0. If the object has returned to its initial point of motion, it does not necessarily mean that the distance covered by the object is 0. You're looking at an object. At a certain time instant, it is at a point. After 10 minutes, you look at the object. The object is still at the same point. You cannot judge its motion between those 2 time instants. In 10 minutes, you cannot say that the object did not move. All you know is that its initial point and final point are same. In between, you did not look at the object. In those 10 minutes, the object could have moved any distance and come back to the same point again. So distance is something that depends on the path. It does not only depend on the initial and final points. Beware of that. Okay. Because it is length, clearly it's a fundamental quantity. Also, its SI unit is nothing but meters. Okay. So that's something you need to learn about distance. Also, one more thing. Let us say an object is at a point A at certain time instant. Let us say t equal to 0. If it moves to B in a given direction, like let us call this direction as positive direction. Let us say it moves to B, which is 5 meters away from A along a straight line. You say the distance covered by the object in the 1 second is 5 meters. If the object moves back in the opposite direction in the second, it comes back to C through 2 meters. Now you know in the first 2 seconds of its motion, the object has traveled a total of 5 plus 2, 7 meters, not 5 minus 2, 3. The object was at A, now it is at C. It has moved through 3 meters in a total of 2 seconds, but it has moved totally 7 meters in 2 seconds. Okay. Basically, what I'm trying to say is if you try to draw a graph between distance and time, when time is increasing, distance can never decrease. When you draw a graph between distance and time, as time increases, the graph of distance versus time can never decrease. What does it mean? Let us say initially the object is somewhere. So obviously it has not moved, so distance is 0. In the first second, it has moved 5 meters. Let us say 5 is here. So you would say the graph would be like this. It has moved from point A to point B. In the second, it comes back in the opposite direction. It comes back through 2 meters. You should not draw the graph this way. This is wrong. It has come back, so the object's distance decreases. No, it does not happen like that. In 2 seconds, the amount of total distance it has traveled would be 7 meters. Not necessarily at the same speed, but anyway. So it would be this point. So if this point is 1, 5, this point would be 2, 7. So this distance object. What if, say, for example, in the third second, from t equal to 2 to t equal to 3, in the third second, if the object was at rest, what would have been the distance versus time curve? It would have stayed horizontal. It did not move. It would have come to 0.3, 7. It will not go up, it will not come down. Basically, remember, any distance versus time graph, right? D versus T graph. Any distance versus time graph is never negative, whenever decreases. Distance versus time graph never decreases. In coordinate system terms, what it means basically is the slope of distance versus time graph is never negative. Slope of a distance versus time graph is either positive or can be 0 at times, but distance versus time graph can never have a negative slope. That is what it means. Okay, so that's all we need to know about distance for now. I hope you understand. If you need a screenshot of this, please take a screenshot. I'm going to clear the board. I'll give you some time. Right? I'm clearing the board now. Here. Now, back to motion parameters. We were discussing motion parameters as those quantities which we measure to describe motion and try to see how it's happening, how fast or how long it has been happening. The first thing that we saw was position. Second thing that we saw is distance. The third motion parameter is displacement, which is quite similar to what is distance. I'll write the symbols here. Our position vector is usually written as small letter r. It's a vector, so r bar. Distance is written as small d. It's a scalar quantity, so it's not a vector obviously. So displacement is written as a capital S, and it is also a vector. Now, because displacement is a vector quantity, how do I define it? Every vector must be specified with the magnitude as well as direction. So when you're defining displacements, of course, you have to specify both of them, right? The definition of displacement: it is a vector whose direction is from initial point to the final point and whose magnitude is the shortest distance between them. Between them, as in between what? Between the initial and final points. What does it mean? Say an object was at A. It has moved to a point B. An object was at point A. It has moved to a point B. Say, for example, the object took a path like this. A to B, it has traveled. It took a path like that. You know that distance is the total length of the path. You have to measure it along the path, the total length of the path taken. But displacement is a vector whose length, whose magnitude is the shortest length between A and B. So this straight line distance here is the displacement, the magnitude of displacement that the object has attained as it went from A to B. Listen, it does not mean that the object actually went along this path. No. The displacement is mentioned as 3 meters long. That does not mean the object has traveled 3 meters. You only say that the object has displaced through 3 meters, right? If the displacement is 3 meters, what does it mean? If the object is from A, was at A, and if somebody says the object needs to be displaced through 3 meters, what do? Just write 3 meters and say the object went here. You don't say the object went along this path. No, the object only went to here. It could have gone in a very random path, right? You just say it has got displaced from A to B, which is 3 meters long. Okay. And what about direction? Of course, direction had to be mentioned. Direction must also be mentioned. Otherwise, 3 meters I can draw this way also in a straight line, right? In fact, out of the plane also I can draw it. So 3 meters displacement must be mentioned along with direction also. And what is the direction of displacement? From the initial point to final point. As simple as that. See, the object is at A, was at A. It went to B along this path. But the points A and B are exactly 5 meters apart along a straight line. You say the displacement of the object is from A to B, which is 5 meters long. The displacement has a magnitude 5 meters. What about the direction of displacement? You say along AB vector. AB vector is a vector that denotes this direction here. Exactly. The arrow mark that I have drawn, that direction is denoted by a vector called AB vector. AB vector is the displacement vector. You can also write it as, like, R bar is sometimes used for position. Sometimes in some textbooks they write small r bar for displacement also. We'd rather write it as capital S bar. S bar equal to R bar. You could write R bar as RAB bar. That basically tells you the position of B with respect to A. This is equal to AB bar. AB bar is also position of B with respect to A. You're trying to look at B from A. See, that's the direction here. Trying to look at the position B from A. And this vector AB bar has a magnitude 5 units, 5 meters. And it has a direction A to B. Understood? Okay. We'll try to look a little more into it. Say, for example, this is the ground level. Okay. A person is standing at the ground level and he's throwing an object from the ground level. So assuming the object starts from here. So the person is so small. The object is being thrown up from here. If this object is thrown up from here, from the ground, then it's probably going to travel a path like this. Okay. No, it would not move to the right or left. I'm just drawing this for convenience sake. So it goes up to a certain maximum height possible of the topmost point, and from there it starts coming down. As it goes up, you describe it as ascent. As it comes down, you describe it as descent. During its ascent, it might cross a point called P. Let us say some point, some random point P. During its ascent, if it crosses a point P, at the point, if you are measuring or if you are describing, studying the motion of the object, if you want to understand what is the displacement, the amount of displacement when it reaches P is this distance, straight line distance from ground to P. That is the magnitude of displacement. The direction of displacement here is upwards, because this is initial point and this is final point up to that. You're only studying the motion there. That is your final point, initial point to final point. This is the direction of displacement, upwards. When it reaches the topmost point, the direction of displacement is upwards because it is above the initial point. This is initial point. Now, during its descent, let us say it is at a point Q, as shown on the screen. It is at a point Q. It is moving down. It is moving down, but it still is above the ground, is it not? The particle is still moving down. It is moving down, but it is still present above the ground. So you would say when measured from the ground, the displacement of the object is still upwards, not downwards. What it means is the direction of motion has nothing to do with direction of displacement. The direction of displacement is always the direction from initial point to final point, irrespective of how the object is moving in that moment. Okay, I'll give you another example. Say this is the path of an object. An object goes like this in this path. This is the initial point. When the particle is here at this point, its direction of motion is given by tangent. This is the direction of motion, this one. But that is not the direction of displacement. The direction of displacement is this. When the particle reaches P from O, irrespective of how it is moving at that moment, the direction of displacement is always from the initial point to the final point at that moment. Sir, if the particle goes to another point, will the direction of displacement change? Of course it does. If the particle goes to another point, will the direction of displacement change? Of course it does. Even if the magnitude of displacement does not change, the direction of displacement can actually change. What do you mean by that? Say, for example, an object is moving along a circular path. Say it started from the center. From center, it started and it went to the circle's boundary and it started moving along the circle. When it is here, the direction of displacement is this. When it is here, the direction of displacement is this. When it is here, the direction of displacement is this. The direction of displacement is always from initial to final point, irrespective of how the object is moving at that moment. The magnitude of displacement is always the shortest distance between the initial point and final point. Understood? Because it is also some distance, displacement also is a fundamental quantity. It has a dimensional formula L, and it is also measured in an SI unit, meter. And of course, it's a vector quantity. It has a direction, and we saw all that. Now, what about graph? If I draw a graph between displacement and time, what can I say about the graph? Can displacement increase with time? Yes, of course. An object moves this way in the first second. An object moves further in the same direction. It only adds up to the displacement. So displacement can increase with time. If an object moves this way for some time, and from next moment it starts moving in the opposite direction, then the displacement becomes this much in the total time, which means the displacement can actually decrease in time. As with an increase in time, there could be a decrease in displacement. Displacement decreases when the object is moving towards the initial point. Displacement increases when an object is moving away from the initial point. And displacement would not change if the object is usually stationary. So displacement graph can have a positive slope, can have a negative slope, can have a zero slope also. Okay, displacement versus time graph can increase or decrease or stay constant. The slope of displacement versus time graph can be positive, can be negative, or zero at times. Right? So that's all we need to know about displacement for now. So try to take a screenshot of the screen if you want. I'll wait for a small time. Done? I'm clearing the board now. Here we go. So back to the list. Motion parameters. Motion parameters we were looking at. We already looked at position, r bar, distance, b, displacement, capital S bar. The fourth motion parameter that we'll learn is speed. We write speed with a small s or v sometimes, small v. We'd rather use small s. Speed is a scalar quantity by definition. Speed is the rate at which an object covers distance. Mathematically, you would say speed is nothing but distance by time. Speed is nothing but distance divided by time. So by the formula, from the formula you understand that the SI unit of speed is meters per second. There are other commercial units like kilometer per hour, and you know that 1 kilometer per hour is equal to 5 by 18 meters per second. How do you convert? You already probably learned in units and dimensions. A kilometer has 1000 meters, an hour has 3600 seconds. So 1 kilometer per hour will have 1000 divided by 3600 meters per second, which comes to 5 by 18 meters per second. Okay, and it's a scalar quantity because it only deals with distance and time, which both are scalar quantities. We have the SI unit and all that. Obviously, it is something that's not a fundamental quantity, it's a derived quantity. Its dimensional formula is L T power minus 1. I mean L power 1 T power minus 1. You understand? Anyway, now that's basically what is speed. But then when I say distance divided by time, can it stay constant? What do I mean? Say at t equal to 0, the object is at A. By the time t equal to 1, let us say the object comes to B, which is 5 meters away from A. In the second t equal to 2, by the t equal to, from t equal to 1 to t equal to 2, let us say the object comes to C, which is 3 meters further. Let us say in the same direction. Let's not worry about direction now. Let us in the same direction. Now you know, the object has covered 5 meters in 1 second in the first second, and it has covered 3 meters in 1 second in the second second. So it was traveling faster in the first second than it did in the second second. So the speed of an object obviously can change when you move, when you go from a point to another point, when you travel from home to school or school back to house in the evening. You clearly know that the speed of your vehicle, whatever vehicle you're traveling in, need not necessarily be constant throughout the journey. It keeps changing. So speed can actually change. So if speed can change, what does this formula exactly give? Say for example, in this interval, the speed is 5 by 1, which is equal to 5 meters per second. In this interval, speed is 3 by 1, which is 3 meters per second. What about the speed during this interval, the whole thing? During the first 2 seconds, what is the speed? And what is meant by that speed? If you try to measure the speed over this whole interval, A to C, t equal to 0 to t equal to 2, you would use this formula, 8 divided by 2, because the total distance traveled is 8. The total time taken is 2. 8 by 2 is basically 4 meters per second. What is this 4? This 4 is what is called as average speed. Which means if you try to use this formula in the box here, I'm highlighting here. You try to use this formula distance by time. What you get is actually average speed. What is average speed? Average speed is speed measured in a time interval. Average speed is nothing but speed measured in a time interval. It is not instantaneous. You don't measure the speed now. You measure the speed from then to now. That way, right? But there are speed measuring instruments in your daily life, right? You would have seen speedometers in your vehicles. Whatever vehicle you are using, you would have seen some speedometers. The speedometers display a reading of speed that is more instantaneous than average. The reading that a speedometer displays is what is called as an instantaneous speed. How is it able to measure an instantaneous speed? And what is meant by a speed at an instant? What is instantaneous speed? How can you measure speed at an instant? First of all, what is an instant? An instant of time or a time instant is a time interval of 0 size. If a time interval has no size at all, what are you going to substitute here? No way. This is not the formula to measure instantaneous speed. That formula gives you average speed. Total distance covered by total time taken always gives you average speed. It is measured over a time interval. Speed measured at a time instant is what is called as instantaneous speed. How is it measured? Newton suggested that if you knew that the object was traveling with constant speed in a time interval, say for example, in 2 seconds of time, the object covered 8 meters from A to C, and you know that the object's speed did not change during this time interval, then even if you measure average speed, it is as good as measuring the instantaneous speed at every instant, because the speed did not change. Because the speed did not change, the speed measured at any instant is basically the same. The speed measured at any instant is going to be average speed. Average of same numbers is still going to be the same number. Correct? So, but if the speed is changing, what do? If the speed is continuously changing and you want to measure the speed at this time instant, t equal to t, let us say. At this instant, I need to measure the speed of now. How do? You have to consider a time interval, t equal to t equal to t dash. You have to consider a certain time interval in which the object's motion is uniform. Uniform as in object's speed does not change. Let us say, if there exists some time interval like this around t, in which the object's speed was constant, then if you measure the average speed in this time interval, it is as good as measuring instantaneous speed at time instant t. How do we measure average speed in this? Measure the distance, calculate the time taken. Time taken would be final instant minus initial instant, t dash minus t. So d divided by t dash minus t basically gives you average speed during this interval. And because the speed did not change in that interval, the average speed is nothing but the instantaneous speed at t equal to t. That's how you do. But what if I don't have such an interval? What if the object speed is continuously changing? Newton suggested that you take so small a time interval from t. So small, like how small? It cannot be defined at all. So small that it cannot be measured easily. How small it is? As small as you would like to. You take a very small time interval. It is called infinitesimally small time interval. It is so small a time that the speed does not change at all. I mean, the speed is changing, But if you take a very, very small time, there is not enough time for the speed to change. You take so small a time that the speed during this interval is not changing at all. Let us say the speed is s at t, and in a time dt, the speed does not change at all. Then the object would basically travel a distance of s into dt. If this is the distance, that divided by time taken dt should give you speed, does it not? So instantaneous speed is something that is measured like this. This is not a practical way of measuring it. I'm just telling you, I'm just giving you a theoretical way to find it. What Newton suggested is that you draw a graph between distance traveled versus time taken. You draw a graph for an object, distance versus time graph. At whatever instant you want to measure the speed of the object, just basically, the distance versus time graph would never have decreased. If anyone has picked that up, that's very good. The distance time graph would never decrease. It will always increase or remain constant. Now, if you want to measure the time instantaneous speed at any point, say at any instant t, then at this point on the graph, basically just draw a tangent and measure the slope of the tangent. The slope of the tangent at that point gives you instantaneous speed. So there is a theoretical way of finding instantaneous speed, and there is another way. There's a practical way, as a theoretical way to calculate average speed. Average speed is measured as distance by time. Average speed is that speed measured in a time interval. Instantaneous speed is that speed measured at an instant. There is a basic difference between those two. All right. So what can we say about speed now? You know that speed can change. So clearly here the slope is basically speed. You know that the distance versus time graph can never decrease, which means its slope can never be negative, right? Slope is nothing but speed now. So speed can never be negative. That's something that we need to know about speed. Speed cannot be never negative. Speed can never be negative. Speed is either 0 or positive. If the object is not moving, its speed is 0. If the object has moved through a certain time interval, then during the time interval, its average speed can never be negative. Cannot be 0 also because it has moved. So there is some distance. So clearly there is some average speed. Now, if an object starts from a point and comes back to the same point in a time interval, even if it has come back to the same point again, its average speed during the time interval is not 0. It is not 0 because speed cannot be negative. It is always 0 or positive. When you take averages, it's never going to be 0 unless it's all 0. So if the object has not moved at all in a time interval, then the average speed of the object during the time interval would be 0, right? So there could be one more questions, concept-based questions or true or false-based questions like these. So they may ask you, what do you understand from the statement average speed of an object is 0 in a time interval? If the average speed of an object is 0 in a time interval, it means distance traveled by the object in the time interval is 0, and therefore the object did not move at all. If distance is 0, the object did not move. The displacement is 0, the object could have moved but has come back to the same point again. Understood? So average speed equals 0 does necessarily mean the object has stayed at rest, has not moved. Okay, so that's all we have to know about speed. So yeah, if you want to take a screenshot, please go ahead. I'll wait for a very small time. All right. So I'm going to clear the board now. Here we go. Back to the list again. Motion parameters. We dealt with position, which is a vector, r bar. We dealt with displacement, which is a vector, s bar, which is nothing but change in position, r2 bar minus r1 bar. We also dealt with displacement. Oh yeah, okay, fine. We dealt with distance, which is distance denoted by small d, which is a scalar. We dealt with speed, which is a scalar denoted by small s. And now we shall deal with velocity, which is denoted by small letter v. V bar is its usual notation. The definition of velocity. Velocity is defined as the rate of change of position. The rate at which the object's position changes is what is called as velocity. So we have already discussed the difference between average and instantaneous. So I'll straight away write here, average velocity is equal to change in position divided by time taken, or symbolically, average velocity is equal to change in position. We write it as delta R bar divided by time taken, or R2 bar minus R1 bar divided by time taken, or displacement vector divided by time taken, because change in position is nothing but displacement. So average velocity is nothing but displacement divided by time taken. So obviously displacement is a vector, and hence velocity is also a vector. By this definition, SI unit of velocity is still meters per second. The dimensional formula is still L power 1 T power minus 1. Right? Now, what if I draw a graph between displacement vector, displacement and time? We understand that displacement versus time graph can increase as well as decrease, and then maybe increase and stay constant and decrease, etc. It can do all those things, right? Which means the slope of the displacement versus time graph can be positive, 0 for a moment, and can go negative, 0 for a moment, can go positive, and then 0 for a moment, and can be negative, 0 for a time interval, and then negative. So slope of the graph is continuously changing. There might be cases where an object is moving with a variable velocity. At this point, at this time instant, if you draw a tangent and measure its slope, what it gives you is instantaneous velocity. At this time instant, if you draw a tangent and calculate velocity, calculate the slope, that will give you instantaneous velocity at that instant. I'll call it V in 2, this is V in 1. At this point, if you draw a tangent and find the slope, you will get instantaneous velocity at that time instant, whatever the time instant is, T3 is. V in 3. Okay, so velocity can be positive, can be negative, and all that. Okay, instantaneous velocity is measured as the slope of displacement versus time graph. Average velocity is measured as the ratio of displacement and time. Total displacement in an interval divided by the length of the interval, duration of the interval, is what gives you average velocity in that interval. Okay, so we understand the difference between average velocity and instantaneous velocity. Now we'll try to look at a small difference between average velocity and average speed. What is the difference between these two? Yes, of course, this is a vector quantity. That's a basic difference, and this is a scalar quantity. Good, as simple as that. And average speed is the distance divided by time. Average velocity is a displacement divided by time. Okay. Now, average speed equal to 0 means the object did not move, because if average speed is 0, then distance would become 0, right? And therefore, the object did not move at all in that interval. If the average velocity is 0, it only means that displacement is 0. And displacement is 0 does not necessarily mean the object was at rest during the time interval. It could have been moving and come back to the same point again, the initial point again, right? So that is the basic difference between average velocity and average speed, right? If the average speed is 0 during a time interval, then it must mean that speed of the object was 0 at every instant in the time interval. You get it? If the average speed is 0 in a time interval, it means the speed of the object, the instantaneous speed of the object at every instant in the time interval must have been 0, because the object did not move at all. If the average velocity during a time interval is 0, it does not necessarily mean that the object was at rest throughout the interval, which means the instantaneous velocity of the object does not necessarily be like 0 at all points. It could be, or it need not be, right? At some points, velocity could be positive, which means the object was moving away from the initial point. At some other points, the object could be like the velocity could be negative, meaning the object is moving towards the initial point, and overall in the total time interval, the average velocity could become 0, right? My teacher used to crack a joke on this, right? So if you're born in a hospital and as you are growing, the hospital grew with you, and the hospital became big enough, and the maternity ward has become, say, the mortuary. Like, it's a dark joke, so bear with me. And if you happen to come back to the hospital at any point, in your life, and you lay on the same bed, it basically means that the average velocity over your whole lifetime till then is basically zero, because your displacement is zero for the whole year, right? So anyway, so that is the difference between velocity and displacement. Velocity is a vector quantity. You see how it depends. What about the direction of velocity? Right? We have seen two velocities: average velocity, instantaneous velocity. What about the direction of these two? Average velocity is nothing but displacement by time taken. So displacement's direction is nothing but the direction of average velocity. So we knew the distance, the direction of displacement is nothing but from the initial point to the final point. So the direction of average velocity over an interval of time is also from the initial point to the final point. The direction of instantaneous velocity is given by these tangents. You need to know the path. If this is a path and the object is here at a certain time instant, and the tangent to the path at that instant gives you the direction of instantaneous velocity at that point. If the object is here, the instantaneous velocity is in this direction. If the object is moving in a circular path, at this instant the particle has a velocity in this direction. At this instant the particle has a velocity in this direction. At this instant the particle has a velocity in this direction. Right? The velocity's direction keeps changing. So if a particle is moving on a circle even with a constant speed, its velocity is certainly changing. You get it? Even if an object is moving on a circle even with a constant speed, its velocity is certainly changing, because the magnitude of velocity is not changing speed, but the direction of velocity is changing. Understood? So there could be another conceptual question here. If I say speed of an object is constant throughout the time interval, does it mean its velocity is also constant throughout the time interval? Not necessarily. You can't say zero. I mean, you can't say no, you can't say yes. Could be, could not be. You don't have enough information to give a certain answer, right? Speed being constant does not necessarily mean velocity being constant. What about the converse? If the velocity is said to be constant throughout a time interval, does it mean the object's speed is also constant throughout the time interval? Yes, because the velocity includes speed. Velocity, I mean, speed is just a part of velocity. Speed is basically magnitude of velocity instantaneously, not average. Magnitude of instantaneous velocity is nothing but instantaneous speed. This is all right. Magnitude of average velocity is not necessarily equal to average speed. Be careful about this. Magnitude of average velocity need not be equal to average speed in a time interval, but at any instant, magnitude of velocity at that instant must be equal to the speed at that instant. Get it? So these are the important things that we need to know about velocity. So if I'll wait for some time, please take a screenshot if you wish to. Yeah. All right. I'm clearing the board. Here we go. Back to motion parameters. I mean, I see the option of adding screens. From the next class, we'll probably do that. Pardon me for this session. Next class, I'll keep adding the screens so you don't have to take screenshots from that, right? Anyway, we had already dealt with position, distance, displacement, speed, velocity, and the last significant motion parameter that we study is acceleration. Among these are all vectors, and this are scalars. Beware. Acceleration is denoted by a bar. Clearly, it's a vector quantity. Definition of acceleration. Acceleration is simply defined as rate of change of velocity. Acceleration is defined as rate of change of velocity by definition, and we already saw the difference between average and instantaneous. So I'll go directly. Average acceleration is equal to change in velocity by time taken. Okay, average acceleration is nothing but change in velocity divided by time taken. So we already see that the direction of average velocity is nothing but the direction of the change in velocity, right? If an object is moving in a particular straight line, its direction could be still changing. It could come back in the same line, right? So the direction could still be changing. But anyway, if it's moving in one particular line, the direction in which the velocity increases is the direction of acceleration. The direction in which the velocity decreases in magnitude is opposite to the direction of acceleration, right? So acceleration is nothing but change in velocity by time taken on a time interval, average acceleration. By definition, you understand that the SI unit is meters per second per second. So meters per second squared. Dimensional formula would be L power 1 T power minus 2. Okay. I mean, there are no more commercial units of this acceleration. This is very commonly used acceleration units. Okay. Yeah. Acceleration is a vector quantity. Its direction is given by the change in velocity. What about instantaneous acceleration? How do I do that? Like we already saw, the instantaneous velocity was given by the slope of displacement versus time graph. Right? Similarly, acceleration's direction is given by the slope of velocity time graph. If the velocity time graph looks like this, acceleration at this time instant is given by the slope of the graph at this time instant. A. Right? At this instant, acceleration is this. At this instant, the acceleration is this. Okay, let us say these are different instants, T1, T2, T3, etc. Right? So the accelerations instantaneously are measured as the slopes of velocity time graph. Average acceleration is measured as change in velocity by time taken. Okay, say for example at t equal to 0, the velocity of an object was 3 meters per second eastwards. Direction needs to be specified. At t equal to 2 seconds, say the velocity of the object is equal to 5 meters per second northwards. Average acceleration during that time interval is nothing but change in velocity v2 bar minus v1 bar by time taken. If we use vectors, it will become very simple. But I don't know if we have already learned vectors or not. So for now, I'll use the diagrams. 5 meters per second northwards would be drawn like this, 5 meters per second. The length of this line is scaled to 5. 3 meters per second eastwards is drawn like this, 3 meters per second. This length is 3 and this length is 5. You want to subtract the initial velocity from the final velocity, right? So this minus this. So this need not be changed, but minus of this would be basically the other direction, this 3. So if you add this 5 and this 3, you basically subtracting this 3 from this 5. So addition of these two vectors gives you this direction. So this is basically the hypotenuse of the rectangle or the diagonal of rectangle. Diagonal of rectangle is something but root of 5 square plus 3 square length. That is the amount of change in velocity during 2 seconds. That divided by 2 is 2. That gives you the average acceleration. Whatever this is, right? 25 plus 9, 34. Root of 34 whole divided by 2 meters per second square is the average acceleration during these 2 seconds. Understood? If you want to use vectors also, it's all fine. 5 j cap. This is j cap. This is j cap. 5 j cap. This is I cap. So minus, subtract it from this. 5 j cap minus 3 a cap. Whatever is the magnitude of this is the change in velocity. And time taken is 2. So many meter per second square is the average acceleration. Okay. Understood, right? Acceleration, there's basically nothing more that you have to know about acceleration for now, right? That's all you have. So again, please take a screenshot. We'll move on to the relations between motion parameters next. I'll wait. All right, so moving on, I'm rubbing the board. Yeah, so we have learned 6 motion parameters: R bar, D, S bar, small s, V bar, A bar. I'm going to use the symbols because There's a point of knowing the symbols to the names. Position vector, distance, displacement vector, speed, velocity vector, acceleration vector. Okay. Now, if you draw a graph between y and x, from this point A to this point B, A is nothing but, say, A is at a point x1 on x-axis, and B is nothing but x2 on x-axis. And let's say A is y1 on y-axis and B is y2 on y-axis. Then point A is nothing but x1 comma y1. Point B is nothing but x2 comma y2. If I draw A and B with a line, the line has a slope. The slope of this line is defined as the amount of rise in this line as you run from A to B. Run is along x-axis and rise is along y-axis. This amount is basically x2 minus x1. This amount here is basically y2 minus y1. The slope of the graph from A to B, slope of AB, we usually denote slope as m, small letter m. M is equal to y2 minus y1 divided by x2 minus x1. See, I'll redraw a graph between y and x. See, the graph is randomly like this. And this point is A, sorry, and this point is B. A is still x1 comma y1 and B is still y1 x2 comma y2. And if you draw a line joining AB, the m here, y2 minus y1 by x2 minus x1, is the slope of this line, not the graph. Understood? The slope of the line here, given by this formula, y2 minus y1 by x2 minus x1, is nothing but the slope of the line AB. It is not the slope of the graph. It is rather the average slope of the graph from point A to point B. From point A to point B, the graph has different slopes. The slope is changing also. It's becoming negative, it's becoming zero, it's becoming positive. The slope of the graph is changing from A to B. The slope of the line AB rather gives you the average slope. MAB is equal to delta y by delta x is the average slope. And you already learned from Newton's suggestion that average slope measured over a very, very small interval of x is what is called as instantaneous slope. See, if you want to measure the slope of the graph at this point precisely, let us say x1, you can call it x dash maybe. Then at this point you have to draw a tangent, and then m dash is the slope at that point. M dash is equal to delta y by delta x at x is equal to x dash as delta x tends to become 0. This interval, there should not be any delta x here. Delta x, even if it's there, it should be infinitesimally small. So small that the slope did not change. So even if you are calculating an average slope, it's basically nothing but the instantaneous. In mathematics, you will learn later in calculus that this whole expression can be basically written as dy by dx at x is equal to x dash. Do not worry about it right now. It's part of calculus. When you learn calculus, you learn this. M dash is equal to dy by dx, instantaneous slope. Right? We'll write it for the reference sake for now. Displacement vector is nothing but change in position. Average velocity is nothing but displacement by time or change in position by time. But instantaneous velocity is given by dr bar by dt. Right? It's not delta r by dt. This is delta r by delta t. This is dr bar by dt. Instantaneous rate of change of position. That is v instant. Average acceleration is nothing but change in velocity by time taken. But this will give you average acceleration, right? This is change in velocity by time taken in any interval. But instantaneous acceleration is given by dv bar by instantaneous acceleration. Okay? Say for example, there is a question like this. Okay, we're stepping into an example. If position of a particle is expressed in terms of time as r bar is equal to 6t cube minus 3t plus 2 meters. That t is in seconds, then its velocity is dash, its acceleration is dash, all such things. Okay, we are trying to find general expressions. So the answer for the first one would be velocity vector v bar is equal to dr bar by dt. So the derivative of this function, derivative of that would be 18t squared minus 3 meters per second. Second one, instantaneous acceleration is dv bar by dt. It is a derivative of v bar. This is v bar. The derivative of v bar would be derivative of this function, which is 36t meters per second square. So if you have not come across derivatives until now, do not worry about this. You will understand it better after learning what is a derivative. But this is contextually right to know, so I have mentioned it here. So that's 10. Okay. So if you want to take a screenshot, I'll wait. We'll move on to relations between motion parameters and different states of motion. I think we can stop the session right now. We can learn motion parameters and relation between motion parameters, motion equations in the next session, whenever it is. Okay. So I'm stopping the session right now. See you.